Welcome back to the deep dive. If you've been on this journey with us, you know we've spent a significant amount of time deep in the theoretical weeds.
Oh, absolutely.
We've been talking about the abstract frameworks of measure theory,
Yeah.
signal algebras, really the true mathematical bedrock of probability,
The heavy stuff.
the heavy stuff. But today, we're making a major transition. We are moving past laying that foundation, and we're starting to build the actual house of practical applied statistics.
Right. This is where it gets real.
This is where all that rigor we've learned turns directly into actionable tools that let us make sense of the world.
And our sources call this the big flip. I love that term. Think about everything we've done up to now. It's all been probability theory.
Right.
And that kind of thinking is inherently, well, it's deductive. We start with known facts. We know the rules. We know the parameters of the system.
Like a die is perfectly fair or a coin is 50-50.
Exactly. We have a known distribution. And from that, we calculate the probability of a specific outcome. We deduce the result from the known causes.
So if the coin is perfectly balanced, what's the chance of getting 7 heads in a row? The rules are given, and we predict the result.
Precisely. Now, we shift into the realm of statistics, and it's fundamentally inductive. We flip the entire question on its head.
Okay.
We start with the observed effect, the data we actually collected, and then we ask, what are the underlying unknown parameters? What's the hidden model that must have generated this specific result?
So we're working backward.
We are working backward from the outcome to the structure. And that entire process, that is the core of statistical estimation, or as the German sources love to say, schätzen. We are trying to find the best possible guess.
Okay, so let's unpack this with a roadmap for today.
Yeah.
We have a dense, but I think a really fascinating path ahead.
I think so too.
Our main target is the maximum likelihood method-ML. We're going to explore its philosophical roots and then see how it applies in simple discrete systems like estimating animal population.
Classic examples.
And then move to more complex continuous ones. Our central mission, the true technical challenge for today, is applying ML rigorously to the normal distribution, the N-Gegner, if you will.
The final boss, for sure.
We're to derive the estimators for the mean, mu, and the variance, sigma squared. And then finally, we have to confront this fundamental conflict that ML creates about variance, the infamous theoretical debate of N versus N1.
It's a great debate. To start, though, we have to be super clear about our core concept, likelihood.
Right.
When we talk about likelihood, especially with ML, the English term sometimes falls a little short of the mathematical intention. A better translation is often plausibility.
Plausibility, okay.
Or, using the language from the sources, Mutmaßlichkeit. We are not searching for the probability distribution of the parameter itself. That's a key distinction.
Why not?
Because conceptually, the true parameter is usually some fixed unknown constant. It's not a random variable with its own distribution. Instead, we're searching for the specific parameter value that makes the observed data we already have the most plausible.
So we're asking, which setting on the dial makes our actual measurement the least surprising?
That's the perfect way to put it, the least surprising.
To make this abstract concept a bit more concrete, let's start with a classic problem that lives entirely in the discrete world, the urn problem.
A favorite. So we have an urn. It contains a total of n equals 10 balls. The number of white balls, which we'll call k, is the unknown parameter we want to estimate.
Okay.
We do one experiment. We draw a small sample of n equals 3 balls, and crucially, we draw them without replacement.
And our observation, the data we collect. Let's say x, the number of white balls in our hand, is 2. So we're holding 2 white balls and 1 black ball.
Right. So we have our observation x equals 2. Now, what does that tell us about k, the total number of white balls in the urn?
Well, it puts some constraints on it, right? If
Yeah.
we drew 2 white balls, k must be at least 2.
Obviously.
And since we also drew 1 black ball, there has to be at least 1 black ball still in the urn. That means k can't be 10.
Correct. So k has to be an integer somewhere between 2 and 9.
And this is where the maximum likelihood approach takes over.
Yes. We iterate through every possible value of k in that range 2, 3, 4, 5, all the way up to 9. And for each one, we calculate what is the probability of observing our data, x equals 2, if that k were the true number of white balls.
And because this is sampling without replacement, the probability is governed by the hypergeometric distribution.
Right. So we use the formula for that, p sub k of x equals 2, where k is the variable we're changing, and x equals 2 is our fixed observation.
Now, that formula, it's a bit complex algebraically with all the combinations. It's k choose 2 times 10 minus k choose 1, all divided by 10 choose 3. But we can just We can crunch those numbers.
We can,
Yeah.
and if we do, we see something interesting. If we guess that K was only 2, the probability of us getting both of them in 3 draws is actually pretty low. It's about 6.7%.
Okay, not very plausible.
Not very. But if we assume K equals 4, the probability of our result jumps up to 30%. If K is 5, it goes to 41.7%.
So the likelihood is increasing.
It keeps increasing until we hit K equals 7. At K equals 7, the probability of observing our exact result, 2 white balls, it peaks. It's 21 over 40, which is 52.5%.
And what happens if we go past 7, say, to K equals 8?
It drops back down. For K equals 8, the probability is 46.7%. So K equals 7 is the winner. That is the parameter setting that maximizes the plausibility of our observation. We'd say our estimate, K hat ML, is 7.
And this brings us back to that critical philosophical distinction you mentioned.
Yeah.
If we look at that list of likelihood values we just generated,
Yeah.
for K equals 2, 3, 4, and so on, they don't add up to 1. Why is that specific fact so vital for us to grasp?
Because it's the difference between probability and plausibility. If those values sum to 1, we'd be saying that K itself is a random variable and we have some kind of probability distribution over its possible values.
Oh, we don't.
We don't. K is the fixed true number of white balls in that urn. It is what it is. We are simply examining a function, the likelihood function, which plots how plausible our observation is for various hypothetical values of K. We're scanning possibilities, not summing up a probability space.
And the maximum likelihood principle just says find the peak of that plausibility function.
That's all it does.
Okay, let's translate this discrete approach into a much more famous and real-world application, the capture-recapture method. I think some sources call it fish in Z, or fish in the lake.
Right. It's used all the time in population dynamics. Biologists, conservationists, they use it to estimate the total population N of a species in a certain area.
How does it work?
It's a pretty straightforward 2-step process. Step 1, you go out and catch a group of fish, let's say K of them, and you mark them in some harmless way.
A tag or something.
A tag, exactly.
Right.
Then you release them. Step 2, you come back later, you catch a second sample of size, let's say N, and you just count how many of those fish, let's call it little k, are marked.
So we know big K, the number we marked, N, our second sample size, and little k, the number of marked ones we found.
Right.
The thing we want to estimate is big N, the total population.
Exactly. And the intuitive approach, what some call the engineer's approach, it just kicks in immediately.
Simple proportionality, right?
Yeah.
You just assume the ratio of marked fish in your little sample, K over N, should be roughly the same as the ratio of marked fish in the entire lake, K over N.
Yes, and if you just solve that for N, you get the quick estimate. N is approximately N times K divided by K.
So if we marked 100 fish, that's K. And our second catch was 50 fish, that's N. And in that second catch, we found 5 marked ones, that's K.
Then your estimate for N would be 50 times 100, which is 5,000, divided by 5, which is 1,000. Simple and elegant.
It feels right. But the big question is, does that intuitive formula actually hold up under mathematical rigor? It's really the most plausible estimate.
And this is where ML gives us the theoretical justification. We model that second catch as a hypergeometric distribution, HNKN, or N, the total population, is the parameter we're trying to estimate.
And since N has to be a whole number of fish, we're back in that discrete maximization space. We can't just use differentiation.
No calculus for us. So we have to use that comparing neighbors trick again. We compare the likelihood of observing our data, K, at a population of N, versus the likelihood at a population of N1.
We look at the quotient of the two likelihoods.
Right. L sub K of N divided by L sub K of N1. If that ratio is greater than 1, it means increasing N made our observation more likely. We're still climbing the hill.
And if the ratio is less than 1, we've gone past the peak, the likelihood is now decreasing.
Exactly. So we're looking for the N right before that ratio drops below 1.
Now, this is the part where it's easy to just skip the math, but I think the logic of the algebra here is really important. Can you walk us through the conceptual result of comparing those two hypergeometric functions?
I can, and you're right, we shouldn't skip it. The hypergeometric formula, when you expand it and then divide it by the term for N1, it looks like a total mess of factorials.
It does.
However, when you simplify that expression, when you set that quotient to be greater than 1 and start canceling terms, almost all the complex factorials just vanish it. They vanish. And you're left with a surprisingly simple condition.
And what's the condition?
The condition that tells you the likelihood is still rising is simply that the parameter N has to satisfy the inequality. N is less than N times K over K.
Wait, so the likelihood increases as long as N is less than the result from our intuitive proportional formula.
That is the core insight. Precisely. Once n hits that value, or just slightly exceeds it, the likelihood starts to decrease. So the maximum value has to be the largest whole number n that still satisfies that increasing condition.
So the maximum likelihood estimate for n is the floor function of that intuitive estimate. We take the result of the engineer's quick calculation and just round it down to the nearest integer.
Yes. N hat is the floor of n times k over k.
And that convergence is,
Yeah.
it's really powerful.
It is. The mathematically rigorous ML Schetzer, derived by comparing adjacent likelihoods, is, except for that necessary rounding, identical to the intuitive result. ML validates the gut feeling. That proportional ratio is, in fact, the setting that maximizes the plausibility of your data.
Okay, so now we make the jump. We're leaving discrete systems, where we had to use that comparison trick, and we're moving into continuous systems, where the power of calculus finally comes back into play.
And for this, let's use the classic biased coin flip. We toss a coin n times and we observe k successes, or hits. The true underlying probability of a hit, p, is unknown. And critically, p is a continuous variable, somewhere between 0 and 1.
Okay, so a fixed number of trials, a probability of success. The underlying model is the binomial distribution, b of np.
But now here's the trick. We view the binomial probability formula, the probability of getting exactly k hits, not as a function of k, but as a function of the continuous variable p. That becomes our likelihood function, L sub k of p.
And the advantage is huge. Because p is continuous, we can find the maximum by finding where the slope is 0. We can use differentiation.
We can finally use our calculus tools. The binomial likelihood function is the combination n choose k times p to the k times 1 minus p to the n minus k.
And since n choose k is just a constant with respect to p, we only need to differentiate the part with the p's in it.
Right, the p to the k times 1 minus p to the n minus k part. We have to use the product rule here. When we do that and we set the derivative to 0, we're looking for the roots of that equation.
And what we end up with is an equation that has 3 potential roots, 3 places where the slope could be flat.
2 of them are just the trivial boundary conditions, p equals 0 and p equals 1. The third, and the most interesting one, comes from solving the inner part of the equation, and it yields our most probable estimate, p equals k divided by n.
So we have 3 suspects for the maximum,
Okay.
p0, p1, and pkn. How do we figure out which one is the true ML estimate?
We just check the edge cases and think about the shape of the function. For instance, if we observed k equals 0 hits, so only misses, the likelihood function simplifies to just L of p equals 1 minus p, all to the power of n. That function clearly has its maximum when p is as small as possible, so p equals 0.
In our formula, KN would give 0n, which is 0. So it works.
It works. And conversely, if k equals n, every single toss was a hit. The function is now L of p equals p to the n. That's maximized when p is as large as possible at p equals 1.
And again, Kn becomes Nn, which is 1, so it holds up.
It holds up.
Okay.
And for the general case, where k is somewhere between 1 and n1, you've got a mix of hits and misses. In that scenario, the likelihood function LP starts at 0 when p is 0.
Because if the probability of success is 0, getting even 1 success is impossible.
Right, and it ends at 0 when p is 1.
Because if the probability of success is 1, getting any misses is impossible.
So the function starts at 0, ends at 0, and it's positive in between. It has to rise and fall, creating a single peak somewhere. And since nln is the only other point where the derivative is 0, that has to be the global maximum.
So the conclusion is rock solid. The maximum likelihood estimator for the probability p is always just k divided by n.
Always. ML has now provided the rigorous justification that the relative frequency is the best possible estimator for the underlying probability.
We see this pattern emerging, right?
To find the likelihood, find the maximum.
Whether you're in discrete space using neighbor comparison or continuous space using calculus, the method is always define L of theta based on your fixed data and find the parameter theta that maximizes it.
Before we move on to the complexity of the normal distribution, let's pause and just formalize the language a bit. We've been using estimator and estimate. Our source material makes a very clear distinction between what it calls the Schetzer and the Schätzwert. Yes, and this distinction is crucial for clarity. The Schetzer, often written with a capital letter, like T is the function itself, it's the formula, the blueprint. For the coin clip, the formula Kn is the Schetzer. It's the rule you use.
Okay, the rule.
The Schätzwert, then, is the concrete numerical result you get when you plug in your actual data. If you flip 100 times and get 55 heads, the Schätzwert is 0.55.
So the Schetzer is the abstract tool, and the Schätzwert is the specific number that tool gives you for your data.
Exactly, and that leads right to the formal definition. The likelihood function, L sub x of theta, is set up with the data x held fixed. Our ML estimate, which we write as theta hat, is simply the specific value of the parameter theta that maximizes that plausibility function.
Okay, so we now know how to construct an estimator based on plausibility. But, as we mentioned in the roadmap, we now have to ask a second really crucial question. Is this ML estimator any good? I mean, in a general statistical sense.
And this shifts our focus entirely to estimator quality. In almost every practical application you can think of, finance, physics, quality control, we are ultimately trying to estimate two fundamental properties of a system.
Its central location and its spread.
Exactly. The expected value, mu, and the dispersion, the variance, sigma squared.
So to talk about quality, we first need to define the traditional intuitive sample estimators that most people already use. And we have to assume our observations, x1 through xn, are independent and identically distributed, or IID.
Right. Each measurement is independent and drawn from the same underlying distribution. The estimator for the mean is the sample mean, x bar. We sum up the observations, we divide by n. It's the arithmetic average we all learned in school.
And then there's the empirical variance, s squared. This measures the average squared distance of each observation from that sample mean, x bar. But here's the famous and kind of peculiar twist. The traditional preferred formula for this variance uses 1 over n1 as the divisor, not 1 over n.
And that choice, that n1, is the entire key to understanding estimator quality. It is put there specifically to make sure the estimator is good. And in this context, good means unbiased. Or, using the very precise term from the sources, Erwartungstreu.
Expectation fidelity. Let's formalize that. What does it mean for an estimator to be unbiased? What does that promise us?
An estimator, theta hat, is unbiased if its expected value is equal to the true unknown parameter, theta. So E of theta hat equals theta.
Okay, what does that mean practically?
Imagine running your experiment an infinite number of times. Each time you calculate your estimate, the Schätzwert, then you average all of those infinite Schätzwerte together. If that grand average is exactly equal to the true underlying parameter you're trying to find, your estimator is unbiased. It means it doesn't systematically drift away from the target. It's fair on average.
And the established theory gives us two critical guarantees based on this standard.
It does. First, the sample mean, x bar, where you divide by n, is guaranteed to be an unbiased estimator for mu. It's fair. Second, the empirical variance, s squared, only maintains its status as an unbiased estimator for sigma squared if, and only if, we divide by n1.
So what goes wrong if an engineer or a scientist naively uses n in the denominator for the variance calculation?
If you divide by n, the estimator is mathematically proven to be biased, or versed. And critically, it systematically underestimates the true variance. Your calculated variance will, on average, always be a little bit too small.
Why does that happen? This is the conceptual heart of the n versus n1 debate. It's about degrees of freedom, right?
It is. The need for n1 comes from the fact that we don't know the true population mean, mu. We can't use it. We have to estimate it using our sample mean, x bar.
And x bar is calculated directly from our data points.
Yes. And by its very definition, the sample mean, x bar, is the value that minimizes the sum of squared deviations for that specific sample.
Ah, I see. Because x bar is tailor-made to fit our current data, the deviations we measure from x bar are naturally going to be smaller than the deviations we would have measured from the true but unknown mean mu.
Exactly. We forced a minimum deviation by choosing the center point based on the data itself. This inherent minimization makes the raw sum of squared deviations look smaller than it ought to be relative to the true center.
So to compensate for this systematic underestimation, this bias, we divide by n1 instead of n.
Right. By dividing by a slightly smaller number, we are artificially inflating the result just enough to correct for the bias, ensuring that our estimator for the variance is, on average, fair and correct.
This sets the stage beautifully for the conflict we're about to see. We have the standard quality criterion of unbiasedness, which requires n1, and we have the MO principle of maximizing plausibility.
To see which principle wins out, we have to confront the ultimate distribution, the normal distribution.
The n-Degner.
The n-Degner. We assume we have n observations by 1 through xn that we believe follow the Gaussian distribution, and we need to estimate two parameters at the same time: the mean, mu, and the variance, sigma squared.
If we try to set up the total likelihood function, L of mu and sigma squared, directly, we run into what we earlier called the monster.
Right. Since the measurements are IID, the total likelihood is the product of n individual Gaussian probability density functions, and it is a mathematically terrifying product.
Each of those n factors has a square root, a constant and exponential term with mu and sigma squared in it. Trying to differentiate that product directly is, well, it's nearly impossible with standard calculus.
Which is why the log likelihood trick is considered such a revelation in statistics.
The log likelihood trick. So instead of maximizing the likelihood function L itself, we maximize the natural logarithm of L, so ln(L). Why is that allowed?
Because the logarithm function is strictly monotonically increasing. If you have two numbers, a and b, and a is bigger than b, then the log of a will be bigger than the log of b, always.
So the parameter values, the mu and sigma squared that make L the largest, will also make the log of L the largest.
Exactly. We haven't changed the location of the maximum, we've only changed the shape of the curve, making it far, far easier to analyze.
And the real magic is in the arithmetic simplification. The logarithm takes that horrible product and converts it into a harmless summation.
That's the key. Thanks to the property that the log of a product is the sum of the logs, let's just watch how that monster dissolves into a manageable sum. The Gaussian density function has two main parts.
Right, the constant prefactor, 1 over sigma root 2 pi.
And the exponential term, e to the minus something.
When we take the log of the product of n of these terms, we end up with the sum of n logs.
And for that exponential term, the log and the e they cancel each other out. We're left with the sum of the exponents. The sum from 1 to n of minus xn minus mu squared over 2 sigma squared. And that's a fantastic quadratic sum that we know how to handle.
Okay, what about the constant prefactor? The 1 over sigma root 2 pi part.
Well, since that prefactor is identical for all n observations, when we sum the logarithm of that term n times, it just becomes n times the log of the prefactor. And using log rules, we can break that down further into components. Minus n times log of sigma minus n times log of root 2 pi.
So the final log likelihood function, ln(L), is just a sum of the squared deviations plus these two simplified constant terms involving n and sigma.
And now finally, we're ready for calculus. We'll start with estimating the mean mu hat. Since we have two parameters, we have to use partial differentiation. So we find the partial derivative of ln(L) with respect to mu, and we treat sigma as if it were just a constant number.
So the terms that don't have a mu in them, the minus n log sigma and the other constant, they just drop out. They go to 0.
Immediately. We were left only with the summation of the squared deviation terms.
Okay, let's walk through that partial derivative step by step. The core term we're differentiating is the sum of minus 1 over 2 sigma squared times xn minus mu squared.
And we're treating minus 1 over 2 sigma squared as a constant multiplier. We apply the chain rule to the squared term. The outer derivative brings the exponent 2 down, so we get 2 times xn minus mu. The inner derivative, the derivative of xn minus mu with respect to mu, is minus 1.
So putting it all together, the original minus 1 over 2 sigma squared multiplier meets a factor of 2 and a factor of minus 1. The 2's cancel out. The two minus signs cancel each other out.
And the derivative simplifies beautifully. We're left with 1 over sigma squared times the sum from 1 to n of xn minus mu. And we set this whole thing to 0 to find the maximum.
Since sigma squared has to be positive, it's a variance, we can safely ignore the 1 over sigma squared prefactor. So we're just left with the requirement that the sum of the deviations from our ML estimate, mu hat, must be 0. The sum of xn minus mu hat equals 0.
It's a beautifully simple requirement. We can separate the sum of xn minus the sum of mu hat equals 0. And here's the subtle little algebraic step that solves it. The sum of mu hat over n observations is just n times mu hat.
Of course. So the sum of xn equals n times mu hat. And solving for the ML estimator for the mean.
You get mu hat ml equals 1 over n times the sum of xn.
The arithmetic mean.
The arithmetic mean. The maximum likelihood principle confirms, yet again, our intuitive choice. For normally distributed data, the arithmetic mean is the single estimator that maximizes the plausibility of the observed sample.
Now for the final, and I think the most crucial, derivation. The variance, sigma squared hat. We go back to our simplified log likelihood function and we take the partial derivative, but this time with respect to sigma.
Right, and this one is technically a little more involved because sigma appears in two different places in the ln(L) function.
Okay, the two terms involving sigma are the constant term, minus n times log of sigma.
And the summation term, minus 1 over 2 sigma squared times the sum of the squared deviations.
Let's do the first one, the partial derivative of minus n log sigma with respect to sigma.
The derivative of log sigma is 1 over sigma, so that just gives us minus n over sigma. Simple.
Okay, now for the summation term. Let's treat the sum of the squared deviations as just one big constant. Let's call it c. The term looks like minus c over 2 times sigma to the minus 2.
When we differentiate sigma to the minus 2 with respect to sigma, we get minus 2 times sigma to the minus 3. The minus 2 cancels the minus 1/2 prefactor, and the two minus signs cancel out, making the whole thing positive. We're left with plus c times sigma to the minus 3.
So setting the total derivative to 0, we combine the two results. We have minus n over sigma plus 1 over sigma cubed times the sum of the squared deviations, and that all equals 0.
We can move the negative term to the other side. So n over sigma equals 1 over sigma cubed times the sum of the squared deviations.
And now we can clear the denominators by multiplying both sides by sigma cubed. On the left, sigma cubed over sigma leaves sigma squared.
So we get n times sigma squared equals the sum of xn minus mu squared. And finally, we just solve for sigma squared hat by dividing by n.
And this is the moment of truth. The maximum likelihood estimator for the variance is sigma squared hat ml equals 1 over n times the sum from 1 to n of xn minus mu hat squared.
And that is the definitive result from the ML principle. Maximum likelihood, the principle of maximizing the plausibility of the data you saw, commands us unequivocally to divide the sum of the squared deviations by n.
But this is in direct contradiction with the quality metric we established earlier. If we want an unbiased estimator, one that guarantees fairness across repeated experiments, we have to divide by n1.
This is the fundamental conflict. The maximum likelihood estimator for the variance, sigma squared hat ml, is systematically biased. It is versert.
So the most plausible estimate for this specific data set is guaranteed to be a systematic underestimate of the true underlying scatter when you average it across all possible data sets.
Yeah.
Why would ML, which seems so powerful, give us a biased result?
Because ML prioritizes maximizing the likelihood function based on the parameters we put into it. When we insert our ML estimate for the mean, mu hat, into that variance formula, we are inserting the center point that best fits this specific sample.
The one that, by definition, minimizes the deviations for this sample.
Exactly. Since that center point, mu hat, inherently minimizes the deviations for this particular sample, the resulting variance calculation based on dividing by n will be too small relative to the true population variance, sigma square.
So the bias of the ML variance estimator is basically a side effect of using the sample mean, x bar, in the calculation instead of the true mean, mu. ML just finds the most plausible value based on the immediate data, and in doing so, it doesn't correct for that systematic error that using x bar introduces.
That's it, exactly. The ML principle, while giving you the most plausible result for what you see right now, sacrifices that long-term guarantee of expected fidelity unbiasedness, which you only get by putting in that algebraic correction of dividing by n1.
And if someone's using a small data set, say n equals 10, the difference between dividing by 10 or dividing by 9, that's a 10% difference. That's a significant bias.
It is. But if n is massive, say 10,000, the difference between dividing by 10,000 and 9,999 is negligible.
So that's the practical context.
Right. For large samples, the two estimators converge, and the ML estimator's bias becomes statistically insignificant. But for a foundational statistician, this tension highlights a deep truth. Maximizing plausibility and guaranteeing expectation fidelity are two distinct philosophical goals, and they do not always align.
That was an incredible exploration. Really tracing the path from these abstract foundations all the way to the practical and yet conflicting results of statistical estimation. Let's try to summarize the key insights from our deep dive into maximum likelihood.
Well, first we established that philosophical pivot from deduction in probability theory to induction in statistics, where ML provides this robust mathematical framework for estimation.
And we saw that it often rigorously validates our best intuitive estimates, like relative frequency for probability and the arithmetic mean for the expected value.
Then secondly, we broke down the analytical magic of the log likelihood trick. By converting that monstrous product of probabilities into a manageable sum, we made complex distributions like the Gaussian accessible to powerful optimization tools like calculus.
It's an essential tool.
It is. And finally, we confronted this deep theoretical tension in variance estimation. The maximum likelihood principle demands division by n to get maximum short-term plausibility, but this gives you an estimator that is fundamentally biased.
Well, to get expected fairness, or unbiasedness, statistical theory mandates that n1 correction, which highlights that our choices in estimation depend critically on which philosophical goal we decide to prioritize.
Exactly.
And this raises an important question for you, the listener, to consider when you're applying these methods to your own data. When you have to estimate a parameter, should you prioritize immediate statistical plausibility, using the ML estimator with N, or should you prioritize proven theoretical fairness, using the unbiased estimator with N1?
And to take it a step further, beyond just these two criteria we discussed today, what other metrics should guide your selection of a good estimator? Maybe things like efficiency, which measures the variance of the estimator itself, or its robustness against outliers. The choice is rarely obvious.
The choice is the beginning of the next deep dive. Thank you for joining us for this exploration into maximum likelihood estimation. We'll see you next time.